the end of the presentation from Mr. Nanda Kumar, then we have the next gentleman from Germany. So one of the most highly technically qualified person. So we have Mr. Sebastian with us today. So I'm sorry if there's a small, yeah. We have Mr. Sebastian today with us. I think it's good morning, Sebastian.
Good morning. Thank you very much for welcoming me.
Yeah, I think it could be a summertime in Germany, if I'm right.
Yes, it's right. Yeah.
Okay. I hope everything fine in Germany. I mean, away from all these COVID scares, what you had in the beginning.
Yeah, thank you. So we are fine that far, and we give the best wishes for a happy Independence Day to India, of course. And stay safe and stay healthy.
Thank you so much for your wishes, and we really appreciate your gesture on that front. And with us today, with Sebastian joining us all the way from Germany, a brief introduction of Mr. Sebastian. Mr. Sebastian is an international business development manager who has been a very highly technically qualified person, who has been in the forefront of all the developments, and today his particular topic is going to talk about is very apt for the situation. So I think I should really congratulate the team of the IPI Chennai chapter for having Mr. Sebastian with us, because he's a very highly qualified person with a very long experience in the technical background, qualified in Germany. So today, Mr. Sebastian would be taking us regarding the automatic optimization of plastic components using CADMOULD and VARIMOS. I think a very interesting topic is there ahead for us to understand, because today when we are talked about automation, we are talking about the robotics. When we are talking about productivity and quality, I think the design plays a very important role, and that's where this particular program of Mr. Sebastian would be throwing upon very important aspects. And I look forward to a wonderful program from Mr. Sebastian. And I now request Mr. Sebastian to take it forward and help us enrich our knowledge. Please, over to you, Mr. Sebastian.
Okay, thank you very much for the introduction. So yeah, I'm very happy to be here this morning in German time, or this noon in Indian time. So thank you very much for giving us the chance to present our simulation tool CADMOULD and VARIMOS. I would like to have a brief introduction on company SIMCON in the beginning. So I will present what is our company doing, what are the topics we are dealing on, and then let's go into really technical details like the application of simulation and automatic optimization for the geometrical optimization, and as well for the handling of NFC for natural fiber compound materials, which is getting also more and more important in these days to have a good economic production. So first, some words about company SIMCON. Company SIMCON was already founded in 1988 as a spin-off of the IKV at the RWTH of Aachen. So we heard it already today from Mr. Ramesh. So they have also a cooperation with the IKV as well as with the AZL. So we are also cooperating with the AZL. We did a tech talk yesterday regarding tape integration and injection molds. So we see we already have a connection here. SIMCON is nowadays 32 years in the market and has gained a lot of experience in injection molding, simulation, and optimization. So we have more than 6,000 software customers worldwide. And we are not only selling and developing the simulation, but we are also doing projects for our customers. So that means we have already done a huge amount of projects together with our really successful customers all over the world. The software itself is 100% made in Germany. Our headquarters is located in Aachen, but we have offices in Pune and Chennai with Mr. Suresh and ZW India, Mr. Anubhav. And so globally, we're working together with a network of resellers. many global leaders are already using our solutions. So you can see really well-known names like Arburg, like Continental. So there are, for example, Bosch also. So there are really a lot of companies using simulation already today, but there are also a lot of companies not using it today, even if they should do it, because the simulation will be one of the main keys for the product development in the next years, because you know product development cycles are shortening more and more. They should be cheaper, they should be faster, and of course with less issues. One important point is, for example, also a cooperation with company Arburg, where we are the first simulation tool running directly on an injection molding machine. So on the new Arburg interface, you can directly run a simulation on the injection molding machine, which will help the people on the shop floor to understand what is happening in the mold. There we can mention that also with Wittmann Battenfeld, so Mr. Nanda Kumar, we joined a project together. We did a project together where we are showing results, at least on the injection molding machine. So we are combined all that we are here today, and so that's also very important, I think, in the injection molding industry to cooperate together. So one of the next slides will show you what you will see today. So we'll show you today how to combine simulation and optimization tools to really improve your injection molding results. And that means you should not only have the software on your side, but you should really use it in a proper way. And that is why I would like to show some things about it. So we have CADMOULD as a simulation tool, and we have VARIMOS as an optimization tool. So that means with CADMOULD simulation, you can, of course, already anticipate results very early, identify your issues, like, for example, weld lines, air entrapment, short shots, like warpage behavior. You can really see if the part you would like to produce will have the quality you will need, or if it will not have the quality. And you can, of course, virtually try to do improvements. That means you can try to change the processing parameters. You can try to change maybe the wall thickness, so the design of the part, the mold setup. So you can try different things and will receive a new result, which might be better or which might be worse. Yeah? With VARIMOS together, we will have an automatic optimization. So that means VARIMOS will automatically search the optimized settings, the optimized solutions for your product. And that is something which is very important today, that you don't only know if your result will be good enough. No, you need to optimize it, of course. I would illustrate it on an example, because that's the best way to show it. We will illustrate it on two examples today. We will have on the left side an example of a drink dispenser from company Brita. So it will be not the drink dispenser, but it will be the filter on the drink dispenser. There we did a geometric optimization, especially on the warpage behavior. And on the right side, you can see a glass compartment. This is a part which is done in a natural fiber component material. And we will there see what we did in a project, because in a project we developed the fiber orientation model. We did some thermal optimization as well as some filling optimization. And that are the two parts where I would like to explain you the possibilities of simulation and optimization. For the first example, for the Brita case study with these filter parts. So what you can see is you have a filter which is used in many drink dispensers for the water purification. And this filter is a pressure sensitive part because the water needs to be filtrated, and it could have a high pressure, and therefore the part, of course, needs to be designed in a very good way, and it needs to resist the pressure. We have very high tolerances, especially due to the reason that this filter is built up by two parts. So you have a bottom part and a cap, and these need to be welded together. And that is something which we will see in the later slides, which caused some issues, and where we help to optimize this part. So the challenge was we had a crucial part in the filler cap which was turning out distorted, which has too much warpage, and we saw that it was probably due to the unbalanced filling. Yeah? So you can see the parts, or you can see that the parts are not filling balanced. You have an unbalanced filling. You can see it on this side of this area of the flow front is not matching with this area of the flow front. So of course, if you inject from the center of the part and the part is not symmetrical at the top, you will not have a symmetrical filling at the bottom. The issue was that due to the fiber reinforced material, the resulting parts were too oval. So they should normally be perfectly round, but they were not. Why do they need to be perfectly round? Because they need to be friction welded. So they need to be welded, and then it is a big issue when the parts are not round. So we had to solve this issue by simulation and try to find a solution where the thing can be balanced. To do this, we used VARIMOS, and therefore I would like to show you how VARIMOS can help you to optimize the geometry. I will guide you through these steps which you need to perform, or which mainly are performed automatically by VARIMOS, and show you what will be the outcome. So first, you need to set up your optimization, of course. To set up your optimization, you can define targets, for example, the balance filling. You can define 3 parameters, and you can define constraints, for example, maximum injection pressure, maximum clamping force, or something similar. The 3 parameters in this case were the geometry, so were the wall thickness of the part. I will show you later. Then you have some steps which are automated by VARIMOS. That means as soon as you have set up the optimization, VARIMOS will automatically set up a DOE, so a design of experiments, to do some simulations in the background automatically with CADMOULD. So it will simulate many variants automatically and get the results. And these results of the different variants will be taken into a mathematical model. And this mathematical model will be able to predict the best geometry distribution or the best wall thickness distribution in this part to reach a balanced filling. Yeah? So something which you could do manually, of course, to test different wall thicknesses will here be automated and will be automatically giving you the best result which is possible. Because even if you find a good solution manually, you're not sure that it will really be the best solution which is possible. So the compute optimized processing parameters, or in this case, geometry features, will be delivered to you. So just to explain a little bit more detailed, for the optimization, you can flexibly define targets, constraints, and 3 parameters. So that means the system is not giving everything automatically, and maybe you are not finding your right targets, but you can define them. So the targets could be, of course, everything which is the outcome from a simulation. So it can be the geometry deviation, can be the cycle time, as we heard today already, that the cycle time is, of course, in today's production, one of the important points. Could be the temperature, the material usage, or anything else which is a target or a result from the simulation. 3 parameters which can be varied and optimized with VARIMOS in order to find a solution are all parameters which can be changed in the simulation. And in the simulation, if you compare it to the real mold existing on the injection molding machine, you have a lot of more parameters which can be varied. So it can be the wall thickness on the injection molded part. It can be the location of the cooling channels, can be the runner system, can be every process parameter. So things you will not try on the machine, or you cannot try on the machine because you would need to build a new mold, can be changed in the simulation, of course. So that means if you begin earlier in the process, in the product development process, to optimize, you will have a better mold in your first production trials. And of course, there might be some constraints like some temperature restrictions, like some clamping force restrictions, which can be a limitation for your optimization. That means the special advantages for VARIMOS compared to just simulation or compared to any other system are that you're highly customizable, so you can achieve your targets across different variables, across many variables, and it can have multivariate targets. So also the targets you can you would like to fulfill are not limited and are only limited to the results you can achieve from a simulation, but that are many results today. So let's have a look how we defined the targets, especially on this part. So especially on this part, we defined the targets with some sensors. So we wanted to have the flow front reaching these sensors at the same time. So that was our target, because if we reach these sensors at the same time, we will have a balanced filling. So that easily explained were the targets on the optimization. Of course, now we need some free parameters. In this case, we defined as a free parameter some areas where the wall thickness was allowed to be changed. So we defined some groups on the part. Like you can see 1, 2, 3, 4, 5 groups on the part, where it was allowed for the optimization system to change the wall thickness, for example, plus minus 0.2 millimeters. And then in the background, VARIMOS was running these optimization ones with CADMOULD and giving out the best result. Yeah. There's one important point. The more parameters you change or you optimize, and the more targets you would maybe like to have, that takes a lot of simulations in the background. Here, CADMOULD is showing its very unique selling proposition, because CADMOULD is the fastest simulation tool on the market. That means the simulation time compared to other systems is much faster, and especially if you need, due to DOE, a large number of variants, CADMOULD can bring in its full potential. And that's why we can optimize really a part within other systems are just maybe doing one simulation. And so that is what is becoming more and more important, that you really can do a full optimization in a very short time, because the time when you will have to deliver the mold or to deliver the part will get shorter and shorter in the next years. Okay, so the result which was achieved with VARIMOS was that you can see the wall thickness needs to be changed in some positions. You can see that, for example, this position the wall thickness changed, here this position the wall thickness changed, and that was suggested automatically by VARIMOS. And the result was that before optimization you know the result already, but after optimization we have a nearly 100% balanced filling, which leads to a really better result afterwards. So just by changing some wall thicknesses in the top of the part in a small way, which was allowed by the customer, we were able to really balance the filling in a really good way, and thereby also to achieve a much better warpage result. So like you can see here, the optimization or the results before are the wet ones which are shown. So that means what you can see in the diagram is a deviation from the target geometry on the radial base. So you can see the maximum tolerance was 0.15, and we had values up to 0.21 or 0.22 nearly. So we were really not round in this part. And after the optimization, just by changing some small wall thicknesses and optimizing the filling behavior with the fiber-oriented or fiber-reinforced material, you can see that the roundness is much better afterwards. And we were really able, or what was important was that the customer was able to really weld the part without any issues, which was very important for him. And one nice other benefit or experience was that we suggested, of course, these mold design with also warpage compensation on this part. And directly after the first tryouts, the parts were ready for the production, which is, of course, not a guarantee, but which is a very good achievement in this special project. In this project, also we achieved some reductions, or we achieved some significant cost reductions, because we were able to shorten the cycle time by 20% and to use 20% less material. To explain this a little bit more in detail, because the figures are quite high. Due to this redesign on mold, we combined the injection molding simulations with a structural analysis, so with a strength analysis. And these strength analysis combined with the fiber orientation from the injection molding simulation showed that the material or the wall thickness of the main part was able to be reduced. And so that's why we were able to save this high amount of material, and thereby, of course, also the cycle time, which was in the end leading to a return of investment on this whole project on only 4 months. and they spent more than 250,000 euros on these projects. So it was a really good example to show. So I would like to go over to the next example now, to the example which is based on a natural fiber compound material. So the glove compartment should be optimized, and the fiber orientation should be handed over to a crash test simulation. So what I explained already in the end of the last example was the fiber orientation, which was used in the structural analysis. Here, one of the targets was to really develop a fiber orientation model for these natural fiber compounds, because these natural fiber compounds with a matrix material of polypropylene and several fibers inside, for example, so not at the same time but tested, like sisal, like cellulose, like flax, they all have a little bit different behavior, and especially different behavior than glass fibers. And so therefore, the fiber orientation model needs to be developed first in this project. Other challenges were the filling optimization as well as the thermal optimization for shrinkage and warpage. So this project was done together with, as you can see, really well-known companies like Ford, like Fraunhofer as a very well-known research institute, and also MAPFAM for the crash test. If it comes up to simulation of the fiber orientation for glass fibers, for long glass fibers, we were already able to do this. For NFC materials, as I mentioned, we developed this together in the approach. So the computational model of the University of Medicine, we did some measurements in thin slices and micro CT measurements, and of course then adapted and validated the fiber orientation model in CADMOULD and calibrated it for these type of fillers and the level of fiber content, so that you can see in the end we produced a simulation which was really able to predict the fiber orientation in this part, the cover of the glove compartment, in a very, very precise way. Here you can see one more point. So we used the CT scans to verify the accuracy, and there was a test design. So this test design was molded in a physical test in different injection molding process parameters and so on. And then we were able to measure at 6 locations and in 7 layers the fiber orientation, and were able to compare it with our simulation results. And as you can see on the right side in the pictures, when you see the measured fiber orientation direction, and when you see the fiber orientation from the simulation, you can see that they are matching very well. And that is just to give you a rough impression how fiber orientation can be measured, how it can be simulated, and how we calibrated it then together. Of course, it is not only about the fiber orientation. Today, it comes also, or the question will also be, how about the shrinkage and warpage behavior of this part? So the mold maker needs to deliver, of course, a very precise mold which can produce parts in the specs which are requested by the customer, and the injection molder also needs to find the perfect process settings which are able to deliver these results. If you do a simulation in front, of course, you will already now know what is your warpage looking like, and you can see that in this example, also with natural fiber compounds, we really were able to achieve a very precise warpage forecast for this part. You can see that in Z direction, the warpage simulated with CADMOULD was 3.4 millimeters, and the measured warpage on the real part was afterwards 3.5 millimeters. So for these kind of natural fiber compound, the word natural means also the deviation of the fibers is of course bigger than the deviation in, for example, a glass fiber compound, because the fibers are a natural product. And so that means based on this background, 0.1 millimeters of deviation in this case are already very, very well, and were enough for the customer. The second point I already mentioned was the simulation, the crash test simulation. So, and the real crash test to compare it. Here we got the support from Ford. So Ford did the crash test on this part, and we did also together with MAPFAM this crash test simulation based are the simulations on the fiber orientation exported from CADMOULD. So that means with CADMOULD, you can export the fiber orientation directly, for example, to ANSYS, Abacus, LS Dyna, and so on. So that means you really can bring in an early stage of the product development, some results which might help, we have seen in the example before, to reduce the weight of the product and thereby also cycle time. Because if you can save in any area material, because you know that the strength is good enough due to the fiber orientation, you will be able to save this material and thereby to save costs, of course, also, and save the environment. One other issue where we which showed up during the simulations was that there might be some filling issues, or not only might be, that there will be some filling issues in the real part. So that already showed up during the simulation, and in the first trials it showed the same results. You can see these end of the whips, so these corners of the whips were not filled completely. One reason was the thin wall thickness, combined with the fiber orientation and the low temperature of the material which was used in these first steps. So there are some parameters joining together which caused these issues, but we were able to find a solution for this. But in general, you can see that for these natural fiber compounds, which were unknown before, we can deliver extremely precise simulation for the filling. You can see these complete glass compartment, and if you compare the simulation results with the short shots done on the machine, you can see that they are nearly matching perfectly together, and that is what we developed for this project for NFC fibers, but we did it also for some other biopolymers. For example, we did it together with IFBB in Hanover in Germany for biopolymers. We have one partner in Finland which is producing the material which is based on a wooden filling in the material. So what would when it comes to optimization on this example, we optimized the discoloration of the parts, and therefore we used VARIMOS for the physical sampling. Until now, I explained that VARIMOS is available for the optimization based on the simulation tool CADMOULD. But VARIMOS can also run optimizations by physical sampling. So that means you will also set up your optimization, means target, parameters, constraints. You will receive from VARIMOS an automatic DOE setup, and then you will have to produce these variants physically on your existing mold and on your existing machine. So that means when the mold is once created, you will go on the machine and do the first trials like VARIMOS suggested. And then you will have parts produced which you can measure. In this case, it was necessary because the discoloration of the parts was not able to be simulated, because the discoloration is no result in a simulation. The discoloration is an issue of maybe some temperatures, for example, and that is what we wanted to discover in this case by physical sampling. After we have measured the color of the parts, we were able to build an automatic model and to computize the optimized process parameters. Yeah? So how does this work? To go ahead, we had the setup of the simulation, so we had optimization. So we had to minimize the discoloration as a target. The free parameter was the temperature, and the temperature must be in a certain target area. Why was it the temperature? Because the discoloration comes from kind of material or natural fiber compound which is burned. So the fibers will start to discolorate when the temperature is getting too high in the material, and then they will have this color which is not which should not be there, and which will of course reduce the quality of the natural fibers and thereby also the strength. So the target was to have a more or less not discolored part, and so that's why we wanted to find out the best parameters for this. We have 3 different temperatures which were used in this trial, and you can see afterwards that we measured on the existing part the green value, and the green value was showing the target value and the lower bound of the tolerance. So only with temperatures lower than 170 degrees or 171 degrees, we were able to produce parts which had a green value which was inside the tolerance. Yeah? So you can see that it is also VARIMOS is also able to predict an area which is outside the original range of the variation or of the production process. So on the next slide, you can see if we take two quality criteria, for example, the peak temperature and the pressure, and as a free parameter, the temperature, it will get more complicated already, because you would like to fulfill two constraints. You will have these quality criteria here. As you can see, the target value should be as low as possible, because if we have the filling pressure as low as possible, it will be better for the selection of the machine. And if we have the temperature as low as possible, it will be better for the discoloration of the part. Yeah? And now you can see that VARIMOS will automatically find out which parameter range will be applicable for which result. So for example, for the filling pressure, it will of course be better to have a higher material temperature. For the maximum temperature in the part, it will of course be better to have a lower temperature. And so that means the permissible temperature range is not fitting very good together, but there is a small range where it is fitting together and where you can fulfill both of your targets. And this feasible zone was then found based on these wheel tryouts we have done together with VARIMOS on the wheel injection molding machine. Yeah. And that is something what we used later in the simulation to do the optimization together with CADMOULD. So then together with CADMOULD, we were able to predict this together. And just to give you a look how this looks in our VARIMOS cockpit, I would like to show you the VARIMOS cockpit in wheel. So that looks like this. One moment. Okay, here you can now see the wheel VARIMOS cockpit. So that is the cockpit of our optimization tool. And you can see on the left side the process parameters like the filling time, the mold temperature, and the melt temperature. So in this example, we took some more free parameters, and we have the quality features on the right side. So you see the maximum flow front temperature and the maximum temperature, because these temperatures were important to not discolor the part. And we have the maximum pressure. Additionally, we took some dimensions, for example, some measurements on this part, the length, the width, the flatness of the part. So we took some measurements. Wet dimensions are out of the tolerance, like you can see, so they are above the tolerance or below the tolerance. The other ones are inside. Yeah? And so now you can see directly if you change any parameter, how these measurements are moving. So the quality features will change. So by just changing the filling time, you can see that there's not a big influence. By changing, for example, the melt temperature, you can see that there's, of course, a big influence on the maximum flow front temperature. So if you rise the temperature, you will have a higher temperature, and the opposite side again. And also the mold temperature will have a small influence on some parameters. But you will not be able to find the optimized result like this. So therefore, we have the optimization button. And when you once click the optimization button, you will get a result which will fulfill all of your targets, and you can see that these are the best settings. So not the lowest filling time, but a little bit more, so 1.1 seconds, but the lowest mold and melt temperature will be applicable to have these results available. So that is something which is very important, because you can have a proof of the quality of your mold already very early in your production process. So just to summarize the advantages for using simulation and optimizing together, that means you will find better solutions. Yeah, so you can optimize part, mold, and process automatically, and you are not limited in your targets. You will get really the optimal solution and not just a good enough solution, like you will maybe be able to do it manually. And one of my favorite points is that you will also find unconventional solutions, because many of our engineers, they are very well skilled, they are very experienced guys, and they have a lot of knowledge. But maybe due to this high knowledge and high experience they gained, they will not try any unconventional solutions, which they maybe have seen in one project that they are not working, so they will never try it again. And our system VARIMOS doesn't know about these restrictions or these unconventional solutions, and it will test it. Of course, it's tailored to your needs. As I explained, you can flexibly define your targets, and you can use simultaneously optimization over a large number of variables. One thing which I maybe have showed in the last slide is that it is easy to understand. So you will get the results in a very simple way. So you will have this cockpit where you have the sliders and can directly see what will happen if you change any parameter, maybe on the injection molding machine or on the other areas. And of course, one of the important points today, we can accelerate your product development process, your mold making, your injection molding, and you can achieve it faster by doing simulation optimization. And just to summarize it, the results which will get better are shorter cycle times, minimized clamping force, and especially reduce of energy use, and maybe also finding better materials in the biocomposites area or natural fiber composite area. That is the summary I wanted to give to you, and yeah, of course, maybe there are any questions. Thank you very much.
Thank you, Sebastian.
Thank you.
Sir.
Okay. Good. Again, thank you, Sebastian. I think a very useful and informative session. Lots of learning for me personally as well. Today you talked about the optimization and then to the level of geometric deviations, how it could optimize, and the shorter cycle times with such precision approach. So it was really a wonderful information. And then when it comes to using of CAD mold simulation, which is one of the fastest, I think that's a big advantage in today's product development cycle, where today in every industry the development cycle has come to such a situation where even the car models, because I represent the car industry, we have to develop the vehicles in less than 2 years from a design to the SOP stage. So this type of simulation in designing the products play an important role. And finally, you also touched upon many of the aspects related to temperature and pressure optimization, how VARIMOS and CADMOULD together would be in a position to give us the best benefit. So it's really a wonderful information. I think a lot of industries can benefit from the way it has been designed, and it will be helpful to all of us. So I think this is a very, very valid topic for today, and I appreciate the panelists for this. And I appreciate Sebastian for spending his time and talking about this wonderful aspect from Germany. Thank you, Mr. Sebastian.
Thank you very much. I need to thank you for hosting us.
Yeah, and with this, I think we are coming to the end of today's topics. We had 3 great topics from great experts from the industry in India and from Germany. I think with the different topics we have carried, is there a little time left over for any question and answers, Muthu-san?
Yes, sir. It is left over. Mr. Arun will take over the question answer, sir.
Yeah. So with that, I thank again the IPI chapter of Chennai, the panelists, the speakers, and everybody for giving me an opportunity to be part of this knowledge sharing event, and a great learning for me. Thank you so much.
Mr. Arun.
Yes. Good afternoon, everybody. So there are a few questions, and I'm sure a few more will be coming up. One question, I think, to Mr. Nandakumar. Let me begin with that. What about operator safety in robots?
Yes. In the current situation, if you go to the Europe and other markets, we are needed for the CE certificated robots, and our robots are CE certified robots for the operator safety. Coming to the India part, that most of the time customer avoid the fencing part, which is mandatory in Europe, which that they avoid the fencing part. What we have done it is we built an internal safety cube inside the robot with the software, where the robot will not function outside that safety cube. This gives more safety for the operator.
Thank you, Mr. Nandakumar. There's one question on the DCIM process. It is already answered, but I want to raise it again for the audience.
Yeah.
What is the output throughput limitation? How about the dispersion process when you compare the standard twin screw extruders?
We studied a couple of parts, and also I will send you the video where we have done, a very typical part today for compounding is, biodegradable. You know that biodegradable, very sensitive material, and it has to be, so that material also we done the testing and run successfully the production. In fact, the disposability or the quality is it's more or less equal to the compounding system. So the throughput rate, because this is not a standalone compounding, so the throughput rate depend on the cycle time. So the cycle time of the molding should match with the compounding time.
Okay, sir. Thank you. One more question for you.
Yeah.
Water injection molding.
Yeah.
Can it be used for products like chairs or crates? Is there any limitation to the size?
There is no limitations. It's only, you need to design the mold, and there is some modification in the machines. You need some software and special screw barrels, like pushback system. So you need a setup nozzle. The screw has to suck back the material like this. So there is no limitation. The limitation is only on the design of the parts.
Okay.
So the mold is designed properly.
Yeah, there's a follow-up question. Would the mold chiller capacity be higher in water injection molding?
See, the water injection system is a complete integrated system where the hot water and cooling water, the whole system is, developed as integrated. So it is a water injection, like a gas injection system. It's a complete system. We cannot use just an outside chiller or outside, water. So it is a standalone system where, it will create a high pressure water during the, purge out of the material. And once we program that, after a certain point, it will switch off and then go into the chilling water. So it is an integrated system. So we can vary both the season, depends on the requirement of the molding. We can vary.
Oh, thank you, sir. I think that answered the question.
Yeah.
Go back to Nandakumar. Automation, is it possible to do it with an older machine?
Yes, we are also doing it with the older machines. It's almost good old machines also we are doing. So some of the old machines doesn't have the interface, but still we can able to make common interface, and we can also able to support for the old machines.
Thank you, sir. Question for Mr. Sebastian. You had mentioned that about 20% of material can be saved. How general is it? Is it an extreme case, or is that 20% a common saving?
Okay, thank you for this question. So I think it's not an extreme. It is possible depending on the design of the part which was done before and on the simulation tools which were used. In this special case, if we have 20% material saving, it's normally due to the combination of simulation for injection molding with the fiber orientation and the strength analysis. So because normally parts are designed with the strength analysis just without considering the fiber orientation. If you consider the fiber orientation in the strength analysis, you can reduce the thickness of the walls in many cases, and thereby also save up to 20% of material, maybe also more, because with a general approach, you will be on the safe side more or less with the thickness of the walls.
Thank you, Sebastian. One last question on the two-platen